about these announcements. I've got homework 4 posted on Blackboard right now, and that'll be due on Monday before class. And then in class at the beginning of Monday, we're going to have a brief quiz covering some of the topics that have been addressed since the midterm exam. That quiz, I haven't written it yet, but my intention is to put both a conceptual question and a problem-solving question on there. And today we're going to start covering Chapter 13, which includes a kind of a grab bag of topics, mostly disinfection, but also things like fluoridation, the lead and copper rule. So we'll talk about those other topics on Friday, but today we're going to primarily focus on the disinfection aspects of Chapter 13. And before we get into that, are there any questions that you've got? Okay. So let's just take a step back and refresh our memory on where we're at in the treatment process. You know, before we disinfect, what's happening. And so, assuming that this is a groundwater that needs softening, we would have gone through some sort of a chemical adjustment process, like the addition of lime and potentially soda as well to remove hardness. Even if we're not softening, there would be the addition of coagulant chemicals to induce particle removal steps like settling and sand filtration. And so we've adjusted the chemical properties of the water, and we've adjusted the physical properties of the water in removing particles. But in spite of the fact that you may have relatively low turbidity units, it's still likely that there are pathogens present, especially if we're getting water from a surface source such as the Ohio River. Because remember, the Ohio River is receiving water from creeks, which maybe has septic discharge. And a lot of septic systems in this area are broken, where they're not actually getting all of the removal of pathogens that ought to occur in an intact septic system. And so all these little creeks that go into the Ohio River have pathogens in them. And upstream of here, there are wastewater treatment plants. And in theory, we shouldn't experience much risk from that because the wastewater that's being discharged into the Ohio River upstream of here has been disinfected before that wastewater entered the river. And so the pathogens aren't necessarily coming from the wastewater treatment upstream, but it's better to be safe than sorry. So that's why we're going to be talking about disinfection, is that even when you go through these other steps, there's still some risk of illness. And just to put it into perspective how big the risk of waterborne illness is, it's one of the leading causes of death in the world. Now, here in the United States, waterborne illness, I mean, you're more likely to get struck by lightning than to die from drinking the water in the United States. But elsewhere in the world, that's certainly not the case. Just to put some numbers to it, cholera, which is very dangerous and when left untreated can have as high as a 90% death rate, had about 250,000 deaths in 2006, which is the most recent year that I found statistics for. Fortunately, most of those were treated, and so the death rate is much lower when they're able to provide supportive rehydration therapy. Typhoid is still a really prevalent waterborne disease across the world, and there were 17 million cases across the globe back in 2000, and of those, more than 500,000 people died. But by far the most dangerous and widespread, from a numerical standpoint, disease is amoebic dysentery. And there's more than 2 million deaths each year across the globe of people who are dying from AWD, which stands for acute watery diarrhea syndrome, which is just simply that, like it sounds like, they can't stay hydrated and they die due to dehydration ultimately. So these are really serious diseases, and it's not surprising that people get ill from them when you think about the type of water sources that a lot of the poorest people in the world have access to, which is to say just really dirty streams in places that don't have much protection and where animals are in close proximity to the water that people is drinking, then illness will surely follow. So waterborne illness is a real problem across the world. Fortunately, here in the United States, when you have bad water quality in the United States, it's national news and the president starts talking about it. A recent example of that, I think, was at Jackson, Mississippi, that had a big water system breakdown, and I think their water system was out of commission for a couple of weeks, and it was front page news because it was such an oddity. And the same thing was true a few years ago in Charleston when the water system was out of commission because of chemical contamination. I mean, it was big news because it's just so rare that we face that risk. So about 80% of the disease in the developing world could be attributable to a lack of clean water. And so that takes into account all of the impacts of not having clean water, which is the direct illness, but then also the lack of sanitation that comes when people can't clean their dishes, can't wash their hands effectively, can't clean their bodies in the same way that you'd be able to with access to clean water. If you look over the world, it's been estimated that about half of the world's hospital beds are occupied by people who are currently sick from sanitation and water-related diseases. And we've already talked about the fact that more than 2 million people a year die due to poor sanitation and unsafe water. So worldwide, it's a real problem. And there are organizations that are making big steps forward in trying to provide clean water to remote communities and people who don't have a lot of money. But where there is instability or deforestation or civil war, those are the places that you're most likely to find outbreaks of cholera, typhoid, amoebic dysentery, places that have experienced natural disasters like hurricanes, typhoons, earthquakes, where the already stretched thin resources are disrupted in any way, then those poor people who have pretty limited access to sanitation in the first place, that limited access is just completely wiped out. So disinfection can be accomplished in a couple of different ways. There are chemical constituents when added to the water, which do an effective job of inactivating or killing bacteria, viruses, and other infectious pathogens. Examples of some typically used chemicals would be chlorine, and different species of chlorines are used, which we'll talk about a little bit. Less commonly would be bromine, which is another halogen, or if you've been camping, maybe you've used iodine tablets before to disinfect small quantities of water. Ozone is an example of a chemical disinfectant, and we'll talk about ozone and its relative benefits and disadvantages. But increasingly, physical methods of disinfection are becoming popular because they offer some advantages related to reduced cost, reduced risk of safety-related issues, like remember how we've talked about chlorine in the past and how a spill of chlorine can be a really dangerous situation. So some of the physical methods of disinfection, like using a membrane that can reject viruses or particles larger than viruses, or thermal distillation, such as when they are desalinating seawater. Obviously, if the water is condensed steam, then it's going to not suffer any problems related to pathogens. But there's an even greater push to start using ultraviolet irradiation as a way of disinfecting drinking water. And maybe calling it irradiation makes it sound scary. It's just essentially light. It's not visible light, but UV rays, the same kind of UV rays that tan your skin, they cause damage to pathogens that renders the pathogens unable to replicate, and therefore they don't make you sick. So we'll talk a little bit about that mechanism of inactivation as well. So whereas these chemical disinfection methods have some risks and disadvantages, the physical ones have some advantages as well, although they've got limitations because none of these physical disinfection methods provide residual protection, which is to say, in the pipe, when the water's coming towards your house, if there's still a little bit of dissolved chlorine in the water, then it could be re-exposed to some contamination, like if there's a break in the line, and still be pure by the time it gets to your house, hopefully. Whereas if there's no residual protection from water that's been treated with UV, then the water could pick up a contaminant along the way from the treatment plant to your house. We've already talked about different logarithmic scales of quantifying removals of chemicals, and it's especially common in disinfection because what we're trying to do is accomplish such a high degree of inactivation or removal. And so if you want 99.99% inactivation or removal or killing of a pathogen, sometimes it's referred to as how many nines of removal. And so 99.99 would be 4 nines, because there's 1, 2, 3, 4 nines there. But if we refer to it as logarithmic removal, LR, then it's just the ratio of influent to effluent and then taking the log of that ratio. And so if we had, let's do an example of that, 10,000 bacteria coming into a basin that we're exposing the bacteria to chemicals like dissolved chlorine, and 9,999 of those bacteria die, and only one of them gets out without becoming inactivated, then that would be an example of 4 logs of removal, because we would have removed 99.99% of the incoming bacteria and only one of them made it through. It can also be expressed on a percent basis, and I think this same equation came up in the membrane lecture from Monday's recording, where percent removal is simply 100 minus 100 divided by 10 to the LR. Well, LR is the log removal. So if you had 4 nines of removal, you'd have LR is equal to 4, and this is just showing that you get that same 99.99% removal if you started with 4 logs of removal. So 4 logs or 4 nines, it means the same thing. Okay, now let's consider typhoid. It takes, on average, 10,000 typhoid to make a person sick. If you ingest a single typhoid, then it could be that the probability that it's going to infect you is really low, because your stomach acid maybe is going to digest it before it gets to you. But by the time you've got 10,000 typhoid in your stomach, one of them is going to get through whatever natural immunity that you've got in your stomach and is going to cause an infection. Now, this is just kind of an order of magnitude estimate. It's not exactly 10,000. It's just, approximately on average about 10,000, and you'll get ill from that. So let's say that we've got a 50 milliliter sample of water, and in that 50 milliliters, we can estimate there's 5.6 times 10 to the 6th typhoid. So that's clearly more than 10,000. So if we drank that 50 mils of water, then that's going to cause an infection. So instead of doing that, which would be a mistake, we're going to try and use chlorine. And let's say that a certain concentration of chlorine is going to provide 3.5 logs of disinfection. So I'm going to pause for a moment and ask that you calculate, first of all, what's the percent removal of 3.5 logs? And then determine how many bacteria are there per milliliter. So what's the concentration in typhoid per ml after disinfection with this chlorine that's providing 3.5 logs? And then finally, how much of this contaminated water could you disinfect with the chlorine and then drink? Like, what's the threshold for an illness? How much could you drink before you get to that 10,000 bacteria that have survived inactivation? Okay, let's look at part A, the percent removal. So the LR is 3.5. So if we know LR is 3.5, we're going to use this formula to find the percent removal. And so So LR is 3.5. That means it's going to be 99.97% removal. And in fact, I want to be more precise than that because I'm going to show you an alternate way of calculating part B. So
968.
Well, I want lots of accuracy. So it's 99.968. 37. That's probably enough. All right. So we'll keep that in the reserve for a second. Any questions on part A? The log removal is just given here. Now, normally you wouldn't be given the log's removal. You'd maybe be given the chlorine concentration, and then they'd have to do some sort of lab tests to determine how does the chlorine respond for this particular water with this particular NTU. But through experimentation or some additional info, we could find out the log removal. Okay, so part B, the bacterial concentration, typhoid per ml after disinfection. So you need to find out the influent concentration to begin with, because I told you the absolute number of typhoid in a 50 ml sample. So the first thing that we're doing here is calculating the influent concentration before inactivation occurs. How many typhoid per ml are there? Okay, so that is 1.12 times 10 to the 5th bacteria per ml. So that means a single ml of this contaminated water would be enough to get us sick. So don't drink it, not yet. We're trying to find out what's the effluent concentration. Now, as I already suggested, there's more than one way to do this part B. One of them is to substitute it into this formula and solve for effluent concentration, or the other is to use the percent removal that you've just calculated. I'm going to illustrate the first part, and I wrote on the board a hint in case maybe the logarithm properties aren't fresh in your mind. So this LR is equal to the log of the ratio. But if you do 10 to the LR and 10 to the log of the ratio, then 10 to the log kind of cancels each other out, and so all you're left with is what's on the inside of these parentheses on the right-hand side of the equation, and then on the left-hand side of the equation is 10 to the LR. So that's what I did here, is I said let's use these logarithm properties, and so it turns out to be 10 to the LR is the ratio of influent concentration to effluent concentration. In other words, we can rearrange that algebraically, and if we're solving for the outflow concentration, meaning the concentration after inactivation has been accomplished, it's going to be influent concentration, bacteria per ml, divided by 10 to the 3.5 power. So there should be 35.4 typhoid in each milliliter. So then let's try it the other way. So the alternate way is that we have 99.96837% removal. Okay, so if we start off with 1.12 times 10 to the 5th bacteria per ml, then let's find out how many are going to be removed. So I'm going to say 1.12 times 10 to the 5th, and then multiply that by 0.9996837. Okay, so then removed is 111,965. 1, 2, 3, 4, 5. Yeah. So then remain is 1.12 times 10 to the 5th minus 1.11965 times 10 to the 5th. So how much remain is just going to be the initial amount, 1.12 times 10 to the 5th. Let's swap them. 35.4 remain, which is the same as if we'd done it this other way, using the logarithms. Okay. Any questions so far? All right, so then the last part that it's asking here is how much of this water after disinfection can you drink to avoid illness? So what could you get away with and not quite achieve that infectious dose? So it turns out that we could, if it takes 10,000 to get sick, and it's 35.4 of these for each ml of water, then you can drink 282.5 ml. That's the borderline. If you take one more sip beyond that, and you've got that magical 10,001 typhoids, and you're going to get sick, statistically speaking. Yeah?
How do they count the number of typhoids in a 15 milliliter sample of water?
What they do is they would dilute it a lot, and then they would probably put that diluted sample of water onto an agar plate, which is just like a nutrient gel, and then they would count how many colonies grew like in a 24-hour period. So they...
They have to sit there with the microscope and just sit there.
You don't necessarily even have to use a microscope. If you dilute something like 10,000 to 1, so you take, like of the contaminated water, if you took 1 milliliter of this and you put it in 999 milliliters of pure water, so now you've got a 1 to 1,000 dilution, and then you put that diluted water out over an agar plate that has a certain area, then however many you count, you multiply by 1,000, and that would tell you how many was in the original 1 milliliter sample. So they accomplish it on a practical basis through dilution. Other questions? Okay. So what's the best disinfectant? The optimal disinfectant has some competing criteria. There's no perfect disinfectant because some of these criteria are at odds with each other. It obviously is supposed to be effective against the type of pathogens and the numbers of pathogens, and it should be effective within a reasonable temperature range and within a reasonable amount of time. So you don't want to have to, it shouldn't be some chemical that requires 50 days of exposure before it kills the pathogens. It should be a quick reaction just so that your contact basin doesn't have to be too large. It should also be able to work over a range of temperature conditions because during the summer months your inflowing water is going to be warm, and in the winter months your inflowing water is going to be cold, and different chemicals have different kinetics at a range of temperatures. And so whatever your disinfectant you're going to be uses, it should be effective over the entire range of chemical quality, composition, and also temperatures. You don't want the disinfectant to be toxic for obvious reasons, meaning toxic to people. Because if it kills bacteria, but it also kills people, then it's not a very effective disinfectant because you're trying to avoid death. And that's why we're disinfecting the water. But unpalatable just simply means it shouldn't taste bad. And unfortunately, there are a lot of communities, particularly in South America, that they'll disinfect the water with chlorine, but the people just don't like the taste of the chlorine. And it is kind of not great, chlorinated water. That's why people prefer to drink bottled water usually, is just kind of the residual flavor of chlorine in the water has an off-putting taste. And so there's a lot of communities that, they're well-intentioned, they add chlorination, people complain, and so they stop chlorinating simply because of the aesthetic reasons. And so there's a way around that. If your water quality is better, then there's less of the taste. And there are some disinfectants that have less of an objectionable flavor than others. But ideally, it wouldn't be either toxic or unpalatable. Should be reasonably priced, safe, easy to store, easy to transport, easy to apply. So just talking about the practical side of things. It must be easy to measure the concentration of it, and it should provide residual protection. So there's no disinfectant that meets all of these criteria. It's always a balancing act, whether it's chlorine or ozone or UV or chloramination. There's just no disinfectant that is perfect on all these criteria. So it's just a balancing act. One of the risks of chlorine is that it's a toxic material that when transported to a drinking water treatment plant provides risk in the journey from where it's produced to where it's consumed. If you've got a rail car full of chlorine and that rail car breaks open, then it's going to devastate neighborhoods within a pretty large area. Even these 1-ton cylinders are really dangerous, and drinking water treatment operators have to be pretty highly trained in how to use like full isolation suits and how to react to chemical spills. One of the criteria was that the disinfection should be relatively quick. And kinetics is the study of the rate of reaction. And there are different models that are used to estimate how quickly disinfection reactions occur. And Chick's law is one that we look at as describing the rate that pathogens are killed. And Chick's law says that as the number of of viable particles decreases, so does the speed of the reaction. And that's known as a first order reaction. A first order reaction is declining with respect to time. The rate of killing decreases when there's fewer and fewer bacteria that need to be killed. So it's a first order reaction. So dN, where n is the number of particles with respect to time, is decreasing. So there's a decreasing rate of particles, and it's proportional to some rate constant k. So if we apply that in the real world, then this is the formula that our textbook introduces as a way to estimate over time the number of particles that are still viable during a disinfection process. So N naught is the number of initial particles that you have at the beginning of disinfection, and N is the number of pathogens at a certain time t. So there is a inactivation rate constant where this k value is a specific k value developed to use in Chick's law. C is the concentration of the chemical that's used, and then N is a dilution factor. So first order kinetics just means the rate of the reaction is affected by the concentration of the particles that are being inactivated. And another really important factor is that there has to be good mixing of the chemical and dispersal into the water that's being treated, because if you're just pouring the disinfectant into one part of a contact basin, but then not mixing it and evenly distributing it, then obviously there could be pathogens that don't get exposed to the chemical if it's not adequately mixed. There are some organisms like spores and different types of pathogens that are relatively large in size that can kind of seal themselves off and go into a protective state that would make it more difficult to inactivate them. And that's why sometimes chlorine and UV are used in concert together for disinfection. Because if you have a hybrid approach of using two different disinfectants, then UV is very good against pathogens that are able to go into a spore mode and protect themselves, but then the chlorine is good for providing residual protection. And so a hybrid approach is becoming more common. So the way that we estimate the integrated exposure to a disinfectant is by the concentration times time approach. So CT is the product of concentration and time. So the idea is you can either have a high concentration of disinfectant and use it for a shorter contact period, or if you had a lower concentration, it would take more time, but some combination of the two is required to ensure that there's appropriate inactivation. So here's just an illustration of two two pathogens that are considered relatively resistant to inactivation, Giardia and Cryptosporidium, are a lot more hardy and strong than viruses or bacteria. And you can see the combination of concentration times time that's required at different temperatures for 3 log inactivation. And so if you had water that was 10 degrees Celsius and you're using ozone, then ozone is very effective against Giardia. You could just use 1.43 milligrams per liter of ozone for 1 minute, and it would give you 3 logs of inactivation. But let's say if you're using chlorine dioxide instead, then you could either use 23 milligrams per liter for a minute, or 1 milligram per liter for 23 minutes, or anything in between. You know, it could be, let's say, you're using 10 milligrams per liter and you'd need 2.3 minutes of exposure at that concentration to get the 3 logs of inactivation. Crypto is even more resistant to inactivation than Giardia. You'll look here, this table is saying just 2 logs of inactivation rather than 3. So 2 logs of inactivation is less removal, and you need much, much higher concentrations of contact time and concentration to get even just this 2 log inactivation. Crypto caused a big infection up in Milwaukee in the late 1990s, and like half of the city got sick from contaminated water over the course of a really rainy weekend in Milwaukee, where what happened was it had been snowy, and then suddenly it warmed up and it got rainy. So all the animal waste from some cattle fields that were adjacent to the water source, because it got wet really quickly, all of this cattle waste went into the lake that Milwaukee draws from for their water source, and it didn't get inactivated all the way, and so a ton of people got really sick. And that was kind of one of the events that kicked off this pressure to have two different forms of disinfection, like trying to join together both a chemical disinfectant and a physical disinfectant. When chlorine is used as a gas, when it's dissolved into water, it forms hypochlorite. And HOCl is a weakly acidic compound that you could either add directly or can form in the water that's being treated by bubbling chlorine gas through it. When chlorine is applied, there's something called breakpoint chlorination, where as you're increasing the amount that has been applied, there is an increase in the residual, but then the residual goes down for a period as the chlorine is consumed by the organic material in the water, but then it begins to go back up again, and it's this free residual past the breakpoint that provides the long-term protection. And so, you know, it's kind of unexpected that you'd be adding more chlorine, but actually the residual concentration is going down. That's just an indicator that the chlorine is being consumed in the process of inactivating pathogens, and sometimes it's also consumed by dissolved organic material, like I've mentioned before, that leaves can decay in surface water, and it provides some organic material that's in the water that is going to get oxidized by the chlorine. Even better than chlorine, chlorine dioxide is being used in a lot of applications. It has to be generated on site because it's relatively unstable, and it's also explosive in high concentrations, and so it's a little bit dangerous. But the advantage that it offers is that it's a much more potent disinfecting agent than just chlorine gas. Part of the reason why it's more potent is because it's selective for small particles. It is so highly reactive that it doesn't generally penetrate into animal cells, but it can still inactivate smaller particles like viruses and bacteria. So whereas chlorine, you wouldn't want to get chlorine on your skin because it'll oxidize you as well as it'll oxidize bacteria. Chlorine dioxide won't oxidize you, and there are some dental applications where they're using it as an antiseptic during oral surgery, and it spares the tissues in the mouth, but it will kill bacteria. So maybe if you've ever swished with hydrogen peroxide, have you ever put hydrogen peroxide on your skin and it kind of bubbles and it stings a little bit? I mean, hydrogen peroxide is an example of something it can kill bacteria, but it's also damaging your cells as well. It's too strong as an oxidizing agent, whereas chlorine dioxide is less reactive to animal cells and is more selective to the things that we actually do want to inactivate. So it's less likely to form disinfection byproducts as well. Okay, we're going to talk about UV on Friday. I want to let you out a couple minutes early because, I kept you late that one time. So for now, just keep in mind that your homework is posted on Blackboard. It's available now. And we'll continue talking about Chapter 13 on Friday.